In this section, we discuss the different aspects about the PID controller design. Now to start with, we need to talk about the different forms of PID controller. Now when you are trying to implement a controller for a process, you need to know what is the given form, because there are more than one form available in implementation of the PID controller. Now first look at the ideal form of the PID controller that we discussed. Now this is also known as the ideal or the textbook form of the PID controller, where we learn that there are three elements. One is the proportional element, the integral element, and the differential element. Now these three elements are there for every form of the controller. However, when implemented, some other aspects needs to be taken care of. For example, for the derivative action, we know that to avoid the derivative kick, in some controller, the derivative action is taken on the output signal and not on the error signal. Now in the ideal form though, we have these three elements in their basic form. So proportional form, where the control action is directly proportional to the error. The integral action is depending on the integral of the error, and derivative action is on the derivative of the error. So in Laplace domain, we get the output in the deviational form as simply KCES 1 over SES and SES multiplied by the corresponding values for the constants. So in the transfer function form, we get this expression US over ES equals KC times 1 plus 1 over tau by S plus tau ds. So this is again known as what is called this ideal or the textbook form of the PID controller. Now if we represent this in the block diagram form, we have this representation where these three elements, the proportional element, the integral element, and the derivative element, are expressed as summation of three outputs from the controller added together, and this multiplied by this Kc because of the representation here that Kc is common for all of these three elements. Now this is also known as what is called this parallel form of the PID controller, simply because the error signal goes through three parallel elements and then they are summed together. Now as we discussed that the derivative controller is implemented along with a filter. So this derivative filter, when the derivative action is taken with the filtered error signal, so we see a filter elements there. So this what is called this PID controller with a derivative filter. So in different software for implementing the PID controller, there are options to include the filter. Now this filter needs another parameters which is user defined. Typically it's some fraction of this tau d. The previous form of the or the ideal form of the PID controller, it shows that the Kc term, it affects all of this proportional, integral, and the derivative component. Now in an expanded form, these three elements are made independent, meaning that there is no common parameter for all of these three elements. So you see here the error signal goes through this Kc and another Ki over S and Kds. Now Kc, Ki, and Kd, this can be chosen independently. Now in the parallel or the ideal version, we have seen that the Kc, the choice of Kc, will affect all of these three elements, proportional, integral, and derivative. However, in this expanded form, there is no constant that affects all the parameters. Now, one advantage of this formulation is that you can independently choose all the parameters, and this is the form that's used in MATLAB. So when you're trying to implement a control in MATLAB, do remember that these three parameters for the PID controller can be chosen independently. Okay. Now we have seen these three forms of the PID controller, which are all represented as parallel elements, meaning the error signal goes through each of the element and the resulting actions are summed together to give the final control action. Now in industries, typically the parallel controller is not applied, rather a series form of the PID controller is applied. Now you see here the error signal goes through this Kc and then the integral term and then a derivative term. So this really represents a Pi component and this represents a PD component. Now, so here we see that the error goes through again the constant proportional term there, and there is a proportional integral component, there is a proportional derivative component. This is for historical reasons. In early analog controllers, it was more convenient to use the Pi and PD in series. That's from the implementation point of view. So now this is even nowadays is commonly practiced. So we have this resulting transfer function to be something like this one, Kc 1 plus 1 over tau is and 1 plus TdS. This is equivalent to implementing a Pi and a PD controller in series. Now it can be shown that these two forms, this parallel form and the series forms, are equivalent for some controller parameter settings. So that's a different mathematical discussion. We're not going into that. However, just for your note that these two are mathematically equivalent. PD component here can also be implemented and typically implemented with a filter. So if you add a filter similar to the one that we saw for the parallel form are also implemented for the series form of the controller. Now these are the main forms of PID controller. So we have seen the ideal form, we have seen the ideal form with a filter, we have seen the expanded form which is used in MATLAB, we have seen the series form which is in industrial setting. We also have some other forms which are dependent on the digital implementation that we'll discuss in a later session. For the purpose of controller design, we need to understand the effect of the different elements on feedback control performance. So you know that there are three elements: the proportional part, the integral part, and derivative part. So these three elements affects the overall control performance in different way. So we need to examine those behavior. Now to do this analysis, we'll use the ideal form of the PID controller. Okay? Simply because this formulation allows easier theoretical analysis. And more importantly, most of the controller tuning methods are based on this ideal form because this is the simplest representation. So we can analyze the performance theoretically, and the block diagram analysis will allow us to do that. Now to look at the effect of different parameters, first we look at the proportional only controller. Now know that proportional only controller, there are only one tuning parameter, which is the Kc. So we see these two performance, that the tracking performance and the regulatory performance. Again, just to recall that tracking performance refers to the performance of the controller in tracking the set point, the process. Now Here you see this is the set point, and we know that for the proportional controller there is always offset. Now see, these are the for three different values of the proportional controller, where this is in the increasing direction of the gain. So you see that as the gain increases, the response becomes faster, and also the offset becomes smaller and smaller. So offset goes down and response becomes faster as Kc increases. So also look at the regulatory performance of the controller, where there is a change in the disturbance. So this is disturbance for this case, and the controller responded to the disturbance. And the purpose of the controller is to bring the process back to the initial value. However, you see that the process moves away from the initial value and it's not brought back to the initial value of the output. Now this is in the direction of increasing Kc. So you see, as the Kc increases, the process is brought back nearer to the previous value. However, it's not at the previous initial steady state. So you see that if there is a disturbance affecting the process, the proportional controller will not be able to maintain the set point. However, as the value of Kc increases, the deviation from the previous initial steady state decreases. For the PI controller, we know that there are two components, the Kc and tau I. Now we see that the tracking performance for the PI controller, for this case, we see that the PI controller can eliminate the offset. So there is a set point change here, and the output reaches to the set point. However, depending on the value of Kc, this is the increasing direction of Kc. Depending on the value of the Kc, the response becomes faster and faster. Now we see the regulatory performance again. There is a change in the disturbance, so there is a step change in the disturbance. We see that the process is brought back to the initial value where initially it was, and depending on the value of Kc, the response is faster in bringing the process back to the initial steady value. So this is the effect of Kc on the PI controller performance in terms of the tracking and regulatory performance. Now, if you look at the other parameter, which is the integral time or the reset time, we see that for this case, again, for the both of the tracking and the regulatory performance, we see that there are three responses here. And we have discussed that integral control may introduce oscillation in the process. So as the value of the tau I decreases, now do remember that here, if the tau I decreases, that represents what is called this aggressive controller. So the value of the tau I decreases, meaning the integral action increases, there may be oscillation in the process. So number one is the largest value of tau I, number two is the in between these two, and number three is the smallest value of the tau I. So do remember that the smaller the value for tau I, the more aggressive the controller and the more the integral action. And more the integral action, the response may be oscillating. The same over here for the regulatory performance. We see there are, this corresponds to 1, this corresponds to 2, and this corresponds to 3. We see that as the tau decreases, meaning the integral action becomes more and more, the process is brought back to the initial steady value when there is a change in the disturbance. However, the response may become oscillating depending on the value of this integral or reset time. Now let's look at the effect of the derivative action on the PID controller. Now for the above cases we have seen for proportional controller, for PI controller, and these two performance are for PID controller. Now if we look at this curve, we have here this represents proportional control. So we see that for the proportional control, the final value is not at the desired value, meaning that the proportional control will always result in an offset. We see that for the integral control, this is the curve referring to PI. So we have seen, so we see a large oscillation of the process. Do remember that these two graphs and the other result that's shown here, they're not for the same process. Okay, they're for different process. So the proportional control, there is an offset. For PI control, there is oscillation, and as the D action increases, the oscillation decreases. Now for all of these three other represents derivative action. Okay. Now the look at the dashed one, that's the for the maximum value of this tau D. So meaning that maximum tau D action, for that we see that the process oscillation is much lower. However, it takes longer time to come back to the steady state. But for other cases, the process comes back to the steady state with less oscillation. Okay. So again, the derivative action reduces the oscillation in the response. The same can be observed here. This is for the proportional controller, which results in an offset, and this one is for the PI with a large oscillation, and all of the other elements represents PID, where the oscillation due to the integral action is reduced due to the derivative action. Now we see the effect of these three parameters on the response of the process. Now this is important to understand, because when you are trying to design a controller, meaning that they were tuning the controller parameters, you need to understand that increasing the elements which way it will affect the process response. Now again, for this analysis, we have used the ideal form of the PID controller. Now let's look at what are the design considerations when you are trying to choose the controller parameters. Now we know that the function of a controller is to ensure that the closed loop system has desirable dynamic and steady state performance. Do remember that the two elements, the dynamic element and the steady state element of the performance. Okay. Now the first thing is what is about this stability. The closed loop system must be stable. So this is the main criteria, that the controller should be able to make the process stable. If that's not done, there is no benefit in implementing that controller. Okay. The second thing about this good disturbance rejection. This is what is we call about this regulatory control. Do remember that although we have given more emphasis on the set point tracking, in day-to-day operation, the disturbance rejection is the more frequent job for the controller, meaning there are lots of changes in the disturbance, and the controller should be able to reject those disturbances and do the regulatory component, which is called this, so regulatory control. The third criteria is the good set point tracking. So the set point tracking should be rapid, smooth, and there should be no offset. So this is the tracking performance of the controller. Again, although this tracking performance and the number 3 and number 4 belongs to the same category, this is especially highlighted simply because the steady state offset should be eliminated. That's one of the criteria for designing controller. The other thing is about the control action. If a controller is very aggressive and tries to move the valve very frequently, that may cause an wear and tear of the final control element, and that may introduce large set of variability in the process which may affect again other component in the process. So the excessive control action should also be avoided. And finally, the robustness, meaning that the process condition may change. The controller should be able to take action for different process conditions. So when there are inaccuracies in the process model, the controller should be able to work although there are variations. So that's what is the robustness. Now we need to remember that these goals can be conflicting and there should be some trade-off between these performances. So one thing is that the performance and robustness are conflicting. So if you may have good performance, but you may lose robustness and vice versa. Also, this good disturbance rejection and set point tracking may not be attained together to the desired extent. Okay. Now, again, a little bit details about the performance and robustness. That a smooth response to disturbance and set point change is required to give what is a good performance of the controller. And this requires reasonably aggressive controller setting. So for performance, we need a little bit more aggressive controller. On the other hand, for robustness, so that the controller perform well for a wide range of process condition and with reasonable model inaccuracy, to achieve that can be obtained by some sort of conservative design of the controller. Okay. So when you have conservative controller, you'll have to sacrifice some performance. However, when you have an aggressive controller, you'll get performance, however, at the expense of the robustness. Okay. So there is always a trade-off between this performance and robustness that you need to consider. And depending on the process, you need to consider whether to make a controller more aggressive or less aggressive, to make a controller conservative or aggressive, depending on the process and what you want the response to be. Again, similarly for disturbance rejection and set point tracking, so a controller may give very good disturbance rejection, however, can lead to large offshoot when it's doing set point tracking. On the other hand, a controller giving good set point tracking may lead to poor or sluggish disturbance rejection. So there is also a trade-off between the disturbance rejection and the set point tracking. Okay. Now, considering all of this, let's look at some of the methods for PID controller design. There are numerous methods to design PID controller. Now, in this course, we are not able to discuss a lot of those. However, we'll try to look at some of the methods which are common and also simple to understand and requires less heuristic. Okay. Now, a set of methods we have listed here. The first one is the direct synthesis method. This one we'll see in details what is that method and how to get the controller parameter based on the direct synthesis method. There is another method which is used in industry. It's called this IMC or internal model control method. So we'll simply see the controller tuning equations for the IMC method. There are other controller tuning relations you see in different software. They will be listed and you can use those relations when you have an explicit process model. So those are nothing but some sort of mathematical equations to get the controller parameter from the model parameters. There are these frequency response techniques which defines the what is called this phase margin and gain margin. We'll see later when I do the frequency analysis of a process. There are some sort of computer simulation based method, meaning that you do some sort of implement the controller in simulation and observe the performance and from certain performance measure, you can choose the controller parameters. And another approach is to online tuning after the control system is installed. So you install the control system, you use some sort of default setting and use some sort of online tuning for the controller. We'll see one particular method which is called this continuous cycling approach. The direct synthesis method, we need two things. One is we need an explicit process model. Okay. So if you have an explicit process model, in the direct synthesis approach, what it is done, a desired closed loop response is defined. The idea is that for this method, we want the output to respond in a certain way when there is a change in the set point. If we define this, that we want the closed loop response to be first order, meaning that if there is a change in the set point, the output should move the same way as the first order process is response. And here you see that the gain is 1 because we want the output to follow the set point. So the gain should be 1. Whatever the change in the set point, the output should have the same change. Okay. Now, if we look at the closed loop transfer function, we know that this closed loop transfer function can be represented by this equation: ys over rs equals gpgc 1 plus gpgc, where gp is the process model, this is the controller. So in this equation, if we define ys over rs, and if we know gp, the only unknown is the gc. So gc can be calculated from this equation if you know the ys over rs and gp. So if we reformulate this equation, we get something like this expression. Okay. Now, if this is known and this is known, then we can find gc and find the controller tuning parameters. So let's look at for the case of a first order process model. So if we have the process model to be k over tau s plus 1, and again the desired closed loop response is given by this transfer function, if you simply plug in the value in this equation, you end up getting a gc something like this one. So now this is our gc we obtained, and now we need to consider what are the parameters, what is the kc, tau y and tau d for this case. Now for doing that, we need to compare it with the ideal form of the PI controller. We know that for the ideal form of the PI controller, gc is given as kc 1 plus 1 over tau is plus tau d s. Now if you compare this equation with the equation that we got for the controller, which is this one, now comparing these two, we get that kc is nothing but 1 over k tau over tau cl, and tau y equals tau and tau d equals 0. So meaning that we get a PI controller, not a PID. Okay. So if we have a first order process and the desired closed loop response is also first order, we need a PI controller with the controller parameters to be kc equals 1 over k tau over tau cl, and tau y equals tau and tau d equals 0. Okay. Now let's look at the case when you have a second order process and we want a first order closed loop response. Now if we do the same analysis, we'll end up getting these values for this PID controller. And we need a PID controller for that, with the parameters to be kc equals 1 over k tau y plus tau 2 over tau cl, tau I equals tau 1 plus tau 2, and tau d equals tau 1 tau 2 over tau 1 plus tau 2. This set of parameters. So when there's a delay in the process, the closed loop response should also have the same delay. If you plug in this equation in obtaining GC, you see that we get again a PI controller where the kc is 1 over k tau plus tau cl plus theta. You saw that for the first order case, this theta was not there because theta was equal to 0. So if you plug in theta equals 0, you get the same expression as you obtained for the first order model without delay. Now in the same way, if you have a second order model, we'll get a PID controller. If you have a second order model with delay, we'll get a PID controller for this case, which can be obtained in the same way. Now, in summary, if the desired closed loop response is first order without delay, when there is a delay in the process, the closed loop response should have the same delay. When there is no delay, the closed loop response does not have also the delay. So if you have a first order, we get a PI controller with this parameter. If we have first order with delay, we get the PI controller with this parameter set, and if you have a second order process with delay, we get a PID controller. Now you see that this direct synthesis method gives the structure of the controller along with the parameters of the controller. So for design means first to define the structure of the controller and then getting the controller parameters, and to see that this approach gives us both. However, the requirement is that you need an explicit process model. Also, you need to define a closed loop response. Now here in this approach, we see this, the tau CL is the user defined parameter. So the user has to define this closed loop time constant, meaning that how fast or how slow you want the process to move. Another approach is what is called this continuous cycling method. Now in this approach, there are step-by-step procedure to follow. So initially, at a steady value, the process is put under what is called this proportional only control for a small value of Kc. Then a small set point change is applied so that process moves away from the set point. Now we see that we're applying only the proportional only control. So in that case, if we make a change in the set point, the process will move away from the initial set point. However, it will not be able to follow the new set point. Now, in this approach, gradually the Kc is increased until the output has a sustained oscillation. Okay. Now, by sustained oscillation, we mean that the process does not have an unstable response, meaning that the output is not increasing continuously. Okay. However, the output should be with oscillation at a constant oscillating value. That's what is called this sustained oscillation with a constant amplitude. So this phenomena is called continuous cycling. Okay. Now, when this continuous cycling happens, the gain at which this phenomena takes place, that's called this ultimate gain. So we need to get the ultimate gain for the process, meaning that at what value of the gain we get a continuous cycling. Okay. So this is physically what it means, that it's between the two conditions, stable and unstable conditions. So it's on the borderline between this condition. Now the period of the corresponding oscillation is called this ultimate period for the process. So we get this two estimates, what is the ultimate gain and what is the ultimate period. So ultimate gain is the proportional gain of the controller for which there is this continuous cycling, and the ultimate period is the period of that oscillation. Now when we get these two, we have some tuning rules. This what is called this Ziegler-Nichols tuning relations to get the controller parameters from these two parameters, namely the ultimate gain and the ultimate period. Now if we look at this relation, again we need to choose the structure of the controller. So when we get those two terms, the ultimate period and ultimate gain, if you want to design a proportional only controller, so for this case, Kc will be 0.5 Kcu. Simply what it means to some extent is that the ultimate gain is the gain for which the process is on the verge of being unstable. So 0.5 Kcu simply refers to where really half of the value for which the process may become unstable. So if that's the case, if you define a proportional only controller. Now if you define a PI controller, in that case the Kc value is 0.45 kcu and the tau I is Pu, the ultimate period, over 1.2. Now if you choose a PID controller, in that case the proportional gain is 0.6 kcu, the tau I is half of this ultimate period and the derivative action is 1/8 of the ultimate period. Okay. Now these values 0.5, 0.45, 0.6, these have some heuristics behind it, simply because this may give the best response based on the experience and based on many implementation. Now look at this, that we have to choose the type of the controller for this case. Now the direct series method gave the controller parameters along with the structure of the controller. And in this approach, we see that this continuous cycling approach, we need to first define the controller structure and then get the controller parameters. So this becomes also one of the user defined parameters. Now another method, what is called this IMC, or internal model control method. Now in this approach, we see that the process might have two components. One is what is called this invertible, one is the non-invertible. Okay, what it simply means that we'll see later what does it mean by open loop stable and open loop unstable process. So if you have an unstable 0, if you invert that, you may get an unstable controller. So to avoid that, first the process model is divided into two components. One is the invertible and the uninvertible, where this G negative is the invertible component and the G positive is the uninvertible part. And when you get that, this GC star, it's simply the invertible part of the controller inverted multiplied by a filter. Now this filter is equivalent to defining the closed loop response. So it's 1 over tau CLS plus 1 power R. That's R becomes another user defined parameter. Now if you get this GC star, this final controller is obtained as GC star S 1 minus G GC star S. Now from the block diagram analysis, it can be shown how this formulation came into play. Now we're not going to detail for that part, because for this IMC method there are tuning rules available in the tabulated form. Typically we directly use those rules. Now if we do this, apply this IMC technique for controller design, see that we take the case of a first order plus time delay model and we define this filter to be 1 over tau CLS plus 1. Okay, this is equivalent to really this DS method defining the closed loop response. And for this delay, we see that we can use the Taylor series to approximate the delay. We need an approximation for that. So if we do that, we end up getting the controller parameters. Resulting controller parameters will be Kc 1 over K tau over tau CL. There should be this theta term here, tau equals tau. Now you see that this IMC method is equivalent to the DS method when you use the Taylor series approximation for the delay. Okay, however, the Taylor series is not the only way to approximate the delay term. So if you use a PID approximation for the delay term, we end up getting a different model structure. In the PID approximation, the delay term is approximated by this, and if we have a process model this and then define the filter to be this, we get a PID controller with this controller parameters. Now we don't see the details about how this came. However, for IMC method we'll be using the tabulated value. So if you know the process model, if you know define the filter, you can get the direct parameters from you can get the controller parameter from tabulated values of the So you see that for controller design, there are a few things to consider. One is what is the form of the PID controller. You need to know how the different control parameters affect the process. You need to know what are the design consideration, the stability criteria, and you need to understand that there is a trade-off between performance and robustness. And finally, you need to, for some methods, you need to specify the controller structure, meaning whether you want to choose a proportional PI or PID controller. And for some methods, for example, the DS method, you get the controller structure along with the controller parameters. Finally, there are a lot of tuning rules, and in different implementation, different forms of the PID controller is used. Again, the final point is that the same rule may not be the best for all process. It depends on the process. So you need to have a good understanding of the process to design a good controller for that particular process.